have another kind of poll. I promise I will not take anything personally that you say. um, and this is all anonymous. So if you want to tell me I suck, I guess you don't have a way to do that. But just a few kind of notes as we start. This is our last official class. This is our last time to earn participation points. So we have 2 more meetings technically. The next one is the test. So your test will go live and I will have that kind of optional extra office hours. So you will have 2 hours of your life to take the test. If you want it to be those 2 hours, it can be. If you want it to be some other time, also fine. The test will become available on Thursday, and then it'll be due the 29th, which is the Sunday before reading day. So you'll have quite a bit of time to do it, including Thanksgiving break. It should look very similar to all our other tests. Open book, open notes, unlimited time after you start it, just 1 attempt. Please don't talk to anyone else in your class. Those are kind of the 2 big things. The only slight difference on this one, for me to monitor how I'm doing, there's 2 questions that you have to answer, 2 short answer questions that you have to answer. They'll say unskippable. Since I dropped 2 scores, some people have been skipping some of them, which has been fine. This one, I might still drop those 2 if your answer is your lowest score, but you cannot not answer them. I need to see them just for my own analysis of myself. But otherwise should look exactly the same as every other badge test. And like I said, it'll become available on Thursday, and it'll be due on the 29th of November, which is the Sunday before reading day. Any questions on that? Yeah.
So then Thursday is our last day to earn points for the badge?
No. So no, I've extended that to the 24th, so our last class meeting. So if you want to keep earning points, you can do that until the 24th, because this badge didn't have 4-day or a weird break, so I gave a few more days for that.
Okay, cool.
That also means, sorry, so next Tuesday, the 24th, when all the badge points are due, will also be our last lab meeting. So if you are working on something, working on getting some last minute points, I will be online from 7:30 till 10 that night to answer questions that you might have.
So today isn't our last day of class?
No, it's just our last day of me lecturing.
Oh, okay.
So yeah. Thursday is the test, so there's no class. And then the last Tuesday, there will be a few people giving poster presentations. So what that'll look like, is that a few people have signed up to give presentations in class. So the kind of idea for this, if you are presenting in class, you do not have to comment on the discussion post ones. So 2 of the points for the final presentation, final poster project are for commenting on your peers' posters. But if you present in class, you just have to submit 1 comment on one other person who presented in class, and then you're good for that part 100%. So that's a reason to sign up for the in-class one. But there won't be any participation points. And if you don't join in with us on that day, you can still comment on the discussion board and earn that part of your final presentation stuff. So we have a few people signed up. If we want to get some more, that would be awesome, but we might end up having a very short class on next Tuesday, depending. Any questions about that? And if you do attend and don't present on Tuesday, you can get one of your discussion board comments canceled out by submitting a comment on the presentations in class. But I will not be posting these on a video afterwards. So if you do not attend in person, you cannot comment on these because you'll have other options for that. Any other thoughts, questions, comments? And I'll send out an announcement with those details again after class. Okay. So if you were curious, planetary science was our favorite badge. That's a good one. I can't argue with that. Oh, we got some of those. Cool. Okay. So today we're going to be talking about some NASA missions. I will point out today will be slightly different. Again, all of these student choice days are looking slightly different than the ones that were not student choice. So my plan for this one, I guess 2 notes. First of all, if you've looked at the study guide for this test, there's nothing about NASA missions on the study guide. That's because I feel like a lot of what I'm going to do today is kind of fact memorizing, and I don't like testing you on fact memorization. So don't feel like you have to take really careful notes here, because I want this to be more of just kind of a fun, here's everything that's happening in the universe. And then how we'll end is I'll put you in breakout rooms and you will get some time to design your own mission with your group. So I've given some kind of costs of different missions, and I'll talk about timelines of the different missions. So as I talk through some of the things that are happening currently, I want you to be more thinking about what you think is the most valuable, what you think we should be doing, and then how you might plan and argue that that mission is worthwhile. So the activity for today is going to be designing your own mission and then writing a little proposal to essentially like Congress or some other funding body about why that is something we should be doing, with a little bit of info with like a timeline, scientific justification, and an estimated cost. So don't feel like you have to take copious notes, just hopefully this is semi-enjoyable and informative and you can think about what mission you think is the coolest. Any questions there before we get started? Okay, so I'm going to focus on 3 different kinds of missions. I'm first going to talk about ground-based telescopes, which technically aren't NASA. That's going to be more NSF, so the National Science Foundation. But I think it's good to point out why we might want to build bigger telescopes on the ground as well. Then I'm going to talk a little bit about the space-based telescopes, so why we would want a telescope in space, and then a few of my favorites that are up there. There are a lot, so we're going to kind of hit up some highlights in today's lecture and not go through everything. And then we'll finish up by talking about some of the interplanetary probes that NASA has launched to explore our solar system and the different planets, asteroids, everything else in it. So the first ground-based telescope I want to briefly mention is one, I'm going to just talk about 2 because these technically aren't NASA missions, I just had to throw them in there, is the Vera Rubin telescope, or the Large Synoptic Survey Telescope, LSST. So this is not NASA, this is the National Science Foundation along with the National Research Council. And it's going to be this fairly large telescope in Chile that will begin to observe the sky in 2022. So this is an image of the current building for the LSST. They're still working on it and hopefully it will begin looking at the sky in 2022, barring all pandemic issues. It's being built in Chile. Chile's a pretty common place to build telescopes because it's fairly arid, it's pretty dry, which is great if you want to do astronomy, because water in the atmosphere is actually really good at absorbing some of the light we want to see. So if you can go somewhere where there's not a lot of water, where it's pretty dry, that's awesome. Chile also has some pretty tall mountains, so we can build up higher. Higher means less atmosphere to look through. Less atmosphere is better. And then these mountains are pretty sparsely populated, so we don't have to worry about light pollution. Another thing I just want to kind of point out really quickly, this is a US funded telescope, but all of the telescopes in Chile always make sure they give about 10% or to 30% of their time to universities in Chile, so astronomers working in Chile. So there's collaboration here, despite being primarily funded by the US, there's collaborations between the countries in which the telescopes are built and the funding agencies. The really cool thing about the LSST is that it will image the entire southern sky every night. So it's a big telescope that's going to survey the entire sky every night. And this is going to produce just a ridiculous amount of data every night. So we're going to get 20 trillion bytes of data every night. So we're used to hearing like gigabytes. This is bigger. Giga would be a billion, trillion would be, 100 times larger than a gigabyte. So one of the issues with the LSST is figuring out how are we going to process all of the data it's going to produce, and how are we going to decide which data we keep and what we throw out, because we cannot actually look at all of the images that the LSST will produce every night. And because it's looking at the entire sky every night, it's going to be really good at noticing things that change brightness. So one of the things it'll be looking for is anywhere where is there a flash of light one night and then that bright thing is gone the next night. So that might be a supernova, or is there a variable star where we're seeing just a change in brightness over time. It's also going to be really good at noticing asteroids, because asteroids move. So that's going to, again, produce a change in the light in different areas of the sky. So pretty cool. Hopefully it should be starting pretty soon and just changing, especially like we call this time domain astronomy. So astronomy where we're looking at the changes in the night sky over time. So the other ground-based telescope I just want to briefly mention is the 30-meter telescope. We talked about, if you came on the Decolonizing Science Day, we talked a little bit about the 30-meter telescope. This is the one that has sparked some controversy because it's potentially going to be built on Mauna Kea, where there's sacred land to the Native Hawaiian people. So whether or not it should be built there is a big question. So if you've seen this in the news, that's probably why. I am not going to pretend like I have an answer to whether or not it should be built there. But we talked about that. If you were here for the Decolonizing Science Day, that was what we talked about. What makes this telescope really exciting is its size. So 30-meter would be the size of the mirror. So that's a 30-meter diameter. I'm a swimmer, so I think of this in terms of swimming pools. Swimming pools are typically 25 yards. So this would be larger than a typical swimming pool. And that's one of the reasons why I wanted to just at least mention ground-based telescopes, is because what we can do on the ground that we can't really do in space is we can build really, really, really big telescopes. So it's hard to launch a 30-meter mirror into space, but it's pretty easy to build one on Earth. So that's one of the benefits to using ground-based telescopes as opposed to space-based telescopes. The other really big benefit to working from the ground is if something goes wrong, you can fix it. Once you're in space, it's a lot harder to fix anything that breaks. And if you get better equipment, if we produce better imagers, better cameras, we can update the equipment if it's on ground. If it's in space, it's a lot harder to do that. So there are awesome reasons to have ground-based observatories. We shouldn't just send everything into space. And the 30-meter telescope, once it is completed, will be able to measure the most distant galaxies, find composition of exoplanet atmospheres, so see if they're habitable, and just all this new kinds of science that we haven't been able to do because we haven't had a telescope this big. So those are my two ground-based telescopes that are coming up that I just wanted to mention. Any questions about them? Let's get into space then. So if you're talking about space, we go to space to observe. The main reason is because our atmosphere, although great for life, is really terrible if you're an astronomer. All of the water in our atmosphere is actually really, really good at absorbing light, especially infrared light. So it means that if you're looking through our atmosphere, you're not going to be able to see as faint of objects as you could if you were in space. So going to space is great because we remove that issue. We remove issues of light pollution from humans. So there's just a lot of reasons why being in space is awesome. And if you're going to talk about space telescopes, you've got to talk about Hubble, because Hubble is just, like I've said here, the OG space telescope, just like really kicks off our ability to changes what we can do in astronomy by imaging more and more distant galaxies and creating these beautiful images of stuff in our own solar system, nearby galaxies, and really distant galaxies. So Hubble really revolutionizes astronomy after it was launched. And it's still going. So it was launched in 1990, and it's still observing space today. So Hubble just recently had its like 30-year birthday, and it's still going, which is very impressive. In those 30 years, Hubble has made 14 million observations and contributed to 17,000 peer-reviewed papers. So like I said, just really a great source of information. The images that Hubble produces are incredible, specifically because it's not looking through our atmosphere. Hubble got a lot of the most detailed images of the planets in our solar system. Some of the most distant galaxies were imaged by Hubble, like what we saw when we did the Hubble Ultra Deep Field activity. And Hubble has also looked at the nearest galaxy, Andromeda, with just better resolution, better than other telescopes have been able to. So Hubble's really done a lot at every scale you could possibly think of. The next space telescope I want to talk about is the Kepler Space Telescope. So this is a space telescope that was really designed to specifically look at exoplanets. So its goal was to look for those transits. So when an exoplanet crosses in front of your star and you see a little dip in brightness, and then as the exoplanet blocks the light from the star. And by looking for those dips, Kepler has found 2,662 different exoplanets so far. So it's been, again, kind of changing the way we view the number of planets in our galaxy. Without Kepler, we wouldn't have been able to discover all of the exoplanets we see. And if you do the exoplanet lab, a lot of the data in that lab is from Kepler. I think last I checked, there were 4,300 exoplanets about detected. So Kepler found more than half of those through this transit method. So just really changing how we view other planets in our galaxy. Unfortunately, Kepler did break down in 2013. So the main way Kepler has changed is that initially Kepler was looking at one field of view. So it was just looking at one area of the sky, which is shown here. This area was chosen because you can see it's just slightly above the plane of the Milky Way. So what that means is that we are not looking through all of the dust in the galaxy, but there will still be a lot of stars within our galaxy in this field of view. So we're seeing a lot of stars and not having to worry about dust. So initially Kepler was just looking at that one part of the sky. But the rotation wheels on Kepler that allowed it to stay pointed in the same direction, I think 2 of them broke. So they couldn't keep Kepler looking at that same area without its rotation wheels. So now it's kind of looking all over the place in the sky. And so it's still detecting exoplanets, just not in this one field of view. So now we call it the K2 mission. So it's like Kepler Part 2. So it's still observing where it can, but a slightly different area of the sky than what it was initially planning on doing. My next space telescope, this one I have to throw in here because it's my personal favorite. This is also where all of the data I work with, or a lot of it, comes from. And that's the Herschel Space Telescope. So that's shown here. Herschel is a infrared space telescope, so it was looking specifically at the far infrared part of the spectra. And this is really important because we can sort of see optical light through our atmosphere. We cannot see infrared light through our atmosphere. Our atmosphere is really good at blocking infrared light. And that's kind of for the same reason that climate change is happening. So greenhouse gases don't let infrared heat out, and they don't let infrared light in. So the more greenhouse gases we dump in the atmosphere, the harder it's going to be for infrared astronomers. But also, we just essentially need to be in space if you want to measure these wavelengths. Some kind of fun things about Herschel. At the time it was launched, it was the biggest space telescope with a mirror diameter of 3.5 meters. And in order to image the infrared, it was cooled with liquid helium. So even though it was in space, they needed to cool down the detector to get it to the right conditions to be able to measure this heat sort of signatures from distant galaxies. So it's still light, but it's this infrared light, and infrared detectors need to be super cooled. So it was cooled to a temperature of less than 3 degrees Kelvin, or negative 455 degrees Fahrenheit. So very, very cold. Another kind of fun thing was that it wasn't orbiting Earth. So most of the space telescopes that we launch orbit Earth. Herschel was orbiting at the L2 point. So that's what's shown here. The L2 point is a place where it's going to be based on the gravity, the contributions of gravity from both the Earth and the Sun. Anything at the L2 point will orbit at the same rate as Earth. So it takes Herschel, despite the fact it has a longer semi-major axis, it's going to go around the Sun at the exact same rate as the Earth. So there's some kind of complicated three-body gravitational stuff going on there. But that means it's just easy for Herschel to pass information back to us because it's orbiting at the same time. And then we can sort of use the Earth to block some of the light from the Sun and kind of, again, keep it at this really cool temperature. Because it needed to be super cooled, it could only last so long. So it died in 2013 and is no longer producing data. And that is especially sad because now we have no far infrared space telescopes. So I'm kind of stuck and I can't get new data very well if I want to expand my research project. But hopefully in the near future, there'll be another one. And there's a telescope on an airplane that looks in the far infrared. And it's not quite as good, but you can get above most of the atmosphere with this telescope on an airplane. Any questions so far? And I should point out, I'm just hitting up a few of my favorites. There are a lot of other space telescopes, but those are some that are already up. I wanted to just quickly discuss at least one, I need to remember, space telescope that will, two space telescopes that will be launched hopefully soon. And the first is the James Webb Space Telescope, often just called JWST. And I'm going to show you a little bit about how James Webb is going to unfold after it launches. So that's what's being shown here. So in order to get a bigger space telescope, it needs to go through this kind of origami-like unfolding after it launches and reaches its position also at the L2 point. So it's going to be another one that's orbiting at this L2 point. It should hopefully be launching in 2021. It was supposed to launch in 2018 and has been delayed multiple times. So there's like a whole crew of postdocs that were supposed to work on JW and are not able to. It's specifically going to look at near infrared light. And because of that, it's going to be really well designed to measure very, very distant galaxies whose light have been redshifted to the near infrared, as well as image exoplanets. So it's going to look for exoplanets and very, very distant galaxies. So this is all the solar shields unfolding, and now we're going to see the mirror unfold. Because of this kind of nice unfolding mechanism, this will be the biggest space telescope once it's in space, with a diameter of 6.5 meters, made out of 18 of these 1.3 meter kind of hexagons. So Herschel was 3.5, Hubble was 2.4, this will be 6.5 meters, so just a lot bigger. Bigger mirror means kind of a bigger bucket to gather light, so you can see fainter objects. The very, very scary thing about James Webb is that because it's at the L2 point, once we launch it, we cannot interact with it. It is too far away. We cannot fix anything that goes wrong. So if all of that complicated unfolding, if something breaks, we are stuck. So there's just going to be around a few months after October 2021, there's going to be a lot of very nervous astronomers watching James Webb to make sure all of that unfolding happens correctly and nothing breaks, and we didn't waste years and years and billions of dollars building this big space telescope that will never work. So hopefully it'll all go fine. But that, like I said, there's going to be a lot of very nervous astronomers watching this unfolding process. The other future telescope I wanted to mention is the Nancy Roman Space Telescope. So this is named after the first woman who was an administrator in NASA. And it's going to be sort of the replacement for Hubble. So Hubble's been doing great, but it's broken a couple times. We've been able to fix it so far, but it's probably not going to last too much longer. So this is kind of what is being built to replace Hubble. It will be similar, look at kind of optical UV and a little bit of infrared light, but we'll have a bigger field of view than Hubble, so it'll be able to take images of a bigger area on the sky. And the launch is set for mid-2020, so again, not too long, but hopefully we'll see it soon. And I threw this image in. This is another one of NASA's kind of, so they have the Exoplanet Travel Bureau posters we looked at. This is one from their Galaxy of Horrors poster set, where one of the things the Nancy Roman Space Telescope is going to look for the distribution of dark matter in our universe by seeing where how galaxies are arranged. So it's going to try to measure the cosmic web, which is what is shown here in a kind of fun, silly way with a giant spider. So those are my space observatories. Any questions on any of that before we jump into interplanetary missions? Okay. So my plan for this part, I'm going to kind of start on the inside of the solar system and walk out. So that's kind of how this is going to be organized. And then I'll hit up a few potential future things at the end. Oh, so there's a question, how does NASA compare to other countries? So NASA is often one of the leading groups. We haven't launched a lot recently. You might have heard in the news lately, the most recent space shuttle launch that brought NASA astronauts to the International Space Station was a private company. So that's kind of an interesting thing to consider. And I'm not going to talk about the ISS and all of that in this, but that's something that's kind of funky. NASA has done a lot in terms of these interplanetary probes. The other really big group is ESA, so the European Space Agency has contributed quite a bit. China is been stepping up recently, but there hasn't been a ton from them in the past. So China and India have both been launching more things into space with kind of a focus on the moon. And I think those are kind of some of the big ones. Australia is part of the European Space Agency, despite not being in Europe, but there's a collaboration there. And those are the main ones that I know of off the top of my head. Any other thoughts, questions? So I should also say, I'm not going to talk about the Apollo missions in this lecture because that would be a lecture in and of itself, but that's also a really good example of a NASA mission. So yeah, it's too much. I wanted to highlight a few things. So you want to do a poster on the Apollo mission, that would be cool. But the first thing, most interior in our solar system is the sun. NASA has sent a few things towards the sun. The most recent one is the Parker Solar Probe. So it reached the sun last year, or got close enough to the sun to start collecting data last year. So it's not going into the sun quite yet. It's just kind of orbiting around the sun fairly close. So a distance of 11.6 million miles, which we can compare. The Earth is at 92 million miles, so pretty close comparatively, closer than Mercury even. Because of this, it's really designed to just stand up to very high temperatures. So it's measured a temperature of 1,134 degrees Fahrenheit on its heat shield, and it can't do a lot because of that. So most of our detectors would break down in these kind of temperatures. So we have to, instead, it's looking at magnetic field lines and studying the solar wind. So far it's been able to, when I played that sound of the sun back in our Stellar Science badge, that was something collected by the Parker Solar Probe. And it's also seen how the magnetic field lines twist in more interesting ways than we had previously been able to study. So magnetic field lines will loop back on themselves more than we realized from the sun, which might tell us something about how solar activity changes over time. So that's the sun. The next closest thing is Mercury, and this is where I have to, if I haven't said this yet, astronomers are the worst at naming things, or the best, depending on your opinion. But the probe that went to Mercury was called MESSENGER. MESSENGER stands for Mercury Surface Space Environment Geochemistry and Ranging. How you get MESSENGER out of that is a good question. If you want to waste some time, Harvard keeps a list of all the bad astronomy acronyms. So you can Google dumb or bad astronomy acronyms and read all of the silly things that people come up with. Yeah, I don't know how they got Fat Boy out of that, but this is, and then you can also really tell that astronomers are nerds because there's things like, let's see if I can find some good ones. Batman is definitely one. Apparently there's some bad words in that one. And then there's Gandalf is one, Sauron is one. So we're the worst, I'm sorry. But MESSENGER is just one of the many examples of this. But despite having a silly name, MESSENGER has kind of changed our view of terrestrial planets by really carefully measuring the surface of Mercury. And it's also how we know that Mercury has that huge iron core. So 70% of Mercury is this iron core. It was also able to detect water on the surface of Mercury, which again was unexpected and kind of changed what we thought about the terrestrial planets. As a little bit of a timeline kind of image, MESSENGER was launched in 2004 and reached Mercury in 2011. It took that long, not because Mercury is far away, more because it also orbited Venus a few times on its way to MESSENGER. So this is the only thing that NASA has sent to Venus, but it only orbited Venus. It did not stay in orbit around Venus for very long. After reaching Mercury in 2011, it orbited Mercury for 4 years and then crashed into the surface of Mercury in 2015. So, but in that time, it gave us changed our vision of Mercury from being this kind of boring rock to this really interesting planet that has volcanism and this crazy core, and just wasn't at all what we expected. Again, this probably could be a lecture in and of itself, so I'm not going to spend a huge time on this, but a big project that NASA has done over the past 20 or so years are the Mars rovers. So this was the big program designed to study Mars. The Mars rovers are these little, missions that landed on Mars and launched and had these little robots. This is a self-portrait of Opportunity. So Opportunity took a selfie of itself and sent it back to Earth. These rovers, one of the big things they did was discover conclusive evidence of water in the past on Mars. So one of the ways we know there was water on Mars is the presence of certain minerals that we don't think could be there without water. So specifically hematite is one of the big ones. And those were discovered by the Mars rovers. The Mars rovers have also been able to look for signs of microbial life on Mars. So far they haven't found anything, but they are still looking. There are 3 that were there, and we now have Perseverance, a 4th rover is on its way to Mars. And just as a kind of cool little visual, Spirit is the furthest traveled of any of these rovers. So this is showing Spirit's path across the surface of Mars. And you can see where it completed its first marathon. So it went 26.2 miles from where it landed to where it reached outside of the Marathon Valley. So Spirit has traveled the farthest, and one of the things it's done is it completed a marathon. But you can kind of tell it did it over multiple days, which is why they're all these days. So not super fast, but very impressive. And just, again, have taught us just a ton about Mars by actually being able to be there and collect rock samples and show that Mars did definitely used to have water, but does not seem to currently have water or any form of life. Before we get out to some of the giant planets, any questions? So I think I flipped Saturn and Jupiter, I'm sorry. But the first thing I want to talk about is the Cassini-Huygens mission to Saturn. So this is 2 parts. Cassini was the kind of overall mission. Huygens was a probe that launched from the Cassini mission to land on Titan. So the Huygens probe is the only thing we have landed on a moon that is not the Earth's moon. So that's kind of a cool little fact. And because it was able to land on Titan, that's how we know that there are methane lakes on Titan. So Huygens landed on Titan and saw these methane lakes and was able to send that data back to us, changing our view of this one moon and giving us a possibility of better idea that there might be life there. Cassini was launched in 1997 and reached Saturn in 2004. So because Saturn is far away, it took about 7 years to get there. But it was able to really it created all these beautiful images of Saturn and its rings. So when we see images of Saturn's rings, a lot of them are from the Cassini probe. It was also able to discover multiple moons of Saturn and get images, the images I showed you of Enceladus, the moon of Saturn that had those ice geysers, those were from Cassini. So just a really, again, just because it was able to get so much closer to Saturn, it was able to see the surface in a new way, see that Saturn does have some pretty interesting weather effects similar to Jupiter, even though it doesn't have the big red spot that Jupiter does, and just better get an idea of the moons around Saturn and how those interact with Saturn's rings. But it was retired in 2017, so it orbited Saturn for 13 years, but eventually did die and crashed into Saturn as well as the MESSENGER probe. And so far, this has been our only mission to Saturn, but hopefully there will be future missions to Saturn as well. Jupiter, sorry, going backwards very briefly. We've sent one thing to Jupiter, and that is Juno. Juno was launched in 2011 and reached Jupiter in 2016. And the reason Jupiter was slightly more difficult to study than Saturn is because Jupiter is just so big and has this kind of crazy strong magnetic field. So it was hard for us to come up with a good way to send detectors into this magnetic field that wouldn't just break right away as they got close to Jupiter. So we had to kind of come up with new ways to measure magnetic fields and gravitational fields that wouldn't, again, just automatically break as they move in and out of Jupiter's magnetic field. But it's been able to get an idea. It's currently still collecting data, so a lot of the research that Juno will produce hasn't quite been finished up yet, hasn't been finalized. It arrived at Jupiter in 2016 and is still orbiting. So it's going to try to measure kind of how the gravitational pull might change at different places around Jupiter and what that might tell us about the formation of our solar system. So that's the overall goal of Juno. One thing it has been able to do so far is it sent back these kind of incredible images of lightning storms on Jupiter. So these flashes here are from lightning in the clouds above Jupiter, which is just cool and fun to think about, that there's like lightning on other planets, and we can see it through things like Juno. Getting out to the edges of our solar system, we have to mention New Horizons, which was a mission beyond Jupiter, to Jupiter and then to Pluto and kind of beyond. It was launched in 2006. It swung by Jupiter for a gravitational assist in 2007, and then reached Pluto in 2015. So had a 9-year journey to get to Pluto. And it's the first thing to image Pluto's surface. So if you see images of this heart on Pluto, that is thanks to New Horizons. Before New Horizons went by Pluto, our best images of Pluto were from Hubble, and they essentially looked like a fuzzy blob. So we didn't know what Pluto was made of. We knew it was there, but that was about it. New Horizons was able to tell us that there are water ices on Pluto, and based on its color, it has these tholins, these red rocks that we see on Pluto's surface. And it was also able to get these kind of images of the different structures across Pluto's surface. After passing by Pluto, it went on to image another planet in this outer part of another dwarf planet, sorry, in the outer parts of our solar system called Ultima Thule, which is a weird kind of chunky thing that has like 2 sides to it. So not only did New Horizons get us these awesome images of Pluto, it also gave us more information about the other dwarf planets out beyond Pluto. Any questions so far? Sorry, to pause there. So just as kind of a summary, NASA has sent Messenger to Mercury that briefly went by Venus, probes to Mars, quite a few, or rovers to Mars. So we've had 3 rovers that have been on Mars and then another one on its way. Cassini went to Saturn, Juno went to Jupiter, and then New Horizons went by Pluto. We haven't really sent anything to Neptune or Uranus yet, so those are New Horizons went by them, but that's New Horizons, I think the Voyager missions went by them, but that's the best we've done for the slush giants out there. In between, so kind of getting back closer to us now, jumping back nearer to Earth, is the OSIRIS-REx mission that landed on the asteroid Bennu. So this happened pretty recently. So OSIRIS-REx, OSIRIS stands for Origins, Spectral Interpretations, Resource Identification, Security, Regolith Explorer, another funky acronym somehow in there. OSIRIS-REx was launched it arrived at Bennu, the asteroid. It was launched in 2016 towards the asteroid Bennu, which it arrived at in 2018. It's been orbiting Bennu for the past 2 years, and then in October, on October 20th, it successfully collected a sample from Bennu, and so that's what this image is here. It's going to show you the view from OSIRIS-REx as we approach this asteroid. It's going to be orbiting it for a while. Eventually it'll tap down, I promise. And so here we go, coming down. And then it's going to tag the surface of Bennu, kick up some of these rocks, some of which are now stored inside of its storage chambers as OSIRIS-REx begins its journey back to Earth. So it's bringing a sample of asteroid back to Earth for us to analyze and see what these asteroids are made of. So just to kind of show this, this is the what happened in that video. OSIRIS-REx lands, kicks up some of this material from the surface of Bennu, the asteroid, and then stores it in these 2 little chambers so it can carry it back to Earth. So this was another thing that astronomers were watching very carefully to see that hopefully everything went right and everything worked. And it did. It almost worked too well. The chambers were so full that they couldn't close initially, but they were able to, as it started its journey back to Earth, get those chambers closed to preserve the material. So we can analyze it and get an idea of what asteroids are made of. That will also tell us a bit. These asteroids, nothing really has changed to the material of these asteroids over time. So by measuring the material on these asteroids, we get an idea of kind of the early composition of the solar system as well. Jumping back to really the far end of our solar system are the 2 Voyager space probes. So these are the only space probes to reach interstellar space. So interstellar outside of the influence of our sun. So this is showing here kind of the solar system, all of the outer planets, and then these kind of 2 sheaths where the sun is kind of dominating the space weather, and then Voyager 1 and 2 outside of those. They were launched in 1977, and then Voyager 1 reached interstellar space in 2012, and Voyager 2 reached interstellar space in 2018. And they determined this based on the amount of solar wind they're detecting. So Voyager 1 and 2 are measuring the solar wind, as well as the rate of galactic cosmic rays. And so when the galactic cosmic rays start going up and the solar wind starts going down, they get an idea that they've exited the heliosheath, the heliosphere, and are in interstellar space. And kind of a fun thing, if you go to their mission page, you can see where Voyager 1 and 2 are. So let me see if I can, you can see looking back outside of the orbit of Neptune and Pluto, quite a bit further than New Horizons is on there as well. So New Horizons is going out from here. See if I can get it to show up. And then you can also, it shows you the exact distance from Earth at any time for both of these 2 things, and then how long they've been traveling. So both of them launched in 1977, so they've been traveling for 43 years, but they have left interstellar space, which is pretty cool. So it's just a constantly updating page where you can check the status of the Voyager missions, which is neat. And just fun to think of the things that we have launched outside of the realm of our solar system. So that's all of our current missions. I want to talk really quickly about a couple future missions within our solar system. But before I do, are there any other questions about any of this? Things that we have done so far? It's another fun little thing. If you have a question, keep typing it in the chat or whatever. But because Voyager 1 and 2 were launched in 1977, the technology available then was like cassette tapes and stuff. So your iPhones are more technologically advanced than all of the equipment on Voyager 1 and 2. So just kind of something funky to think about. But like I think they like might have used like 8 tracks partially to store data. So there's these like things that are the way Voyager is sending data back is it's 1977 style. So it's like very different than what we would use today. But it's working. We're still getting, you can see we're still getting data from them, still coming in. The rate of cosmic rays. Cool. Okay. So I'm just going to talk briefly about 2 future missions that I am super jazzed about. The first one is the Europa Clipper mission. So this is NASA's version. There's 2. Europa Clipper is NASA's version. JUICE would be the ESA version of kind of a similar mission that is currently being brainstormed. And this would be a mission to study the moons of Jupiter. So all of those places that I talked about potentially having life. So Europa Clipper is sent to launch in 2025, probably an aspirational date, but maybe, and travel to Europa to search for signs of extraterrestrial life. So the idea would be that the Europa Clipper would measure the composition and the thickness of the ice sheet on Europa to look for signs of, to figure out how much radiation might be getting through this ice sheet, and also look for signs of those organic materials, those SNAPs, that we think are necessary for life to exist. So look in the cryovolcanic eruptions for signs of organic material. JUICE, like I said, is ESA's mission, so the European Space Agency's mission to go to Europa, as well as some of the other icy moons of Jupiter, and JUICE stands for Juicy Icy Moons Explorer. Hopefully that'll happen. I'm excited about that. And then the last thing that I have to mention is the Artemis mission. So like I said, I didn't really talk about Apollo because I felt like that could be its own lecture and didn't want to take up all the time talking about that. But we reached the moon back in the 1960s. With the Apollo mission. Artemis would be the first time we returned to the humanity to the moon. So we've sent other probes to the moon, but we've never sent a person to the moon since the Apollo missions. So the other cool thing about Artemis is that it would be the first woman on the moon. So far there have only been men who have walked on the moon. This would, one of the goals of Artemis is to have the first woman walk on the moon. And it would be another human space flight outside of just going to the ISS. So going somewhere slightly further away, the moon is further away than the ISS, with a vision of kind of starting to think about whether or not it's conceivable to send humans to Mars as well. So if we can get to the moon, maybe set up a space base there and start thinking about how we might get humans eventually to Mars. The goal of the Artemis program would be to land humans on the moon in 2024 and then expand lunar explorations throughout the 2020s. But all of this is really dependent on the development of a new space launch system, the SLS program, which uses a new type of engine, the RS-25, that provides a larger thrust so we could launch more material, more heavier rockets into space. So just a little kind of infographic. What we can see here is this is the space shuttle. So this is what we would have taken astronauts to the International Space Station compared to the SLS, and then compared to the Saturn V. So Saturn V is what took the Apollo astronauts to the moon. So SLS is slightly shorter, but it's about than the Saturn V, but it's about a little over 1 million pounds heavier than the Saturn V. And it's able to have this larger weight because it has these new, more efficient rockets. So if this all works out, if we can get the SLS working, then we'll be able to send more equipment and just a heavier rocket up, and we will be able to launch humans towards the moon, hopefully in the next 4 or so years. So a cool thing on the horizon that will hopefully be happening soon, so we can start getting humans into space again in new and more exciting ways. So that is my brief or not so brief overview of some current, past, and future NASA missions. And now it is going to be your guys' turn to think about what we should be focusing our money, resources, time, and energy on in terms of these NASA missions. So in your assignments page, there is a design a mission assignment that has a link to this discussion page. And your guys' goal is going to be design a mission that, based on some of what I've said, but also everything we've learned so far in our semester, what you think is the most useful thing. Should we be building telescopes that can see more and more distant galaxies to get a better idea of the future, the fate of our universe? Should we be focused on getting a space probe to Enceladus, because right now nothing is doing that and we should go there? Should we really be focused on getting to Mars, getting humans to Mars so we can think about populating other planets? Or maybe should we try to get something into Venus? So there's lots of options here. But I want you guys to brainstorm about that and come up with a little timeline, a bit of a budget, and then a scientific justification. And your scientific justification needs to be to a funding body. So think Congress. How would you take it to Congress and say, this is what we should be spending our money on because it's cool and we should learn this? So I'm going to go ahead and open breakout rooms. This is what we're going to kind of do for the rest of our time, so till 12:50. As I open breakout rooms, does anyone have any questions? The other thing I'm going to say is that I only need one plan per group. So this is going to be one where I really encourage you guys to talk and discuss together. If you would rather work on your own and do your own group, this might be a good time to just sign off and do this on your own time. So, but I'm going to encourage you to work and talk together and then submit one thing